double integrals using polar coordinates. And this is really an instance of, secretly, this is an instance of something called change of variables. Change of variables, which is something like U substitution. It's the higher dimensional analog of U substitution. Okay. So let's recall, right, you have Cartesian coordinates. Right? You have Cartesian coordinates, you have the plane, and you express it as a real line cross a real line, right? So the plane, doesn't, a priori doesn't have any coordinates on it, but you put coordinates on, you assign coordinates to each point, right? By putting on the plane a pair of a pair of copies of the real line at 90-degree angles, right? And then to every xy, to every point on the plane, you associate two numbers, right? X and y, given by projecting perpendicularly down onto these axes. Right? Okay. For polar coordinates, one does something like this. You have the plane again, but we realize the plane as something like the positive real numbers cross the circle. Okay, so you have a circle on the plane, right? You have a circle on the plane, and then you have this ray going out from it, right? You have this ray going out from it, and then for every point, you associate an angle, right? Sorry, I should do this first. You associate the distance from the origin, right? You associate the distance from the origin, so you have this, you draw this big circle, right? Figure out what the distance from the origin is. That's the same thing as this, of course, from this. And you also look at the angle here, right? And you call this thing r theta. Okay. So instead of xy, you have this point r theta. Okay. And for me, I'm going to, when I write the polar coordinates, I'm going to put them in brackets just to distinguish, to let you know that that's a point described using the polar coordinates, right? Okay. Okay. So recall the connection between these two coordinate systems, right? If I have a point phi theta, and I want to describe it using the Cartesian coordinate system, then that's the same thing as r cosine theta, r sine theta. And if I have a Cartesian point, and I want to describe it using the polar coordinates, then the r is going to be x squared plus y squared to 1/2, right? The distance to the origin, and then the angle will be tan inverse of y over x. So what's the point? For us, the point will be that certain regions are more easily described using polar coordinates. Okay. So for example, have a circle, right? Circle of radius A. Okay, how do I describe that using Cartesian coordinates? Right. If I want to describe it using Cartesian coordinates, one way would be to describe it as an x-simple region, right? So in Cartesian coordinates, you would say, well, this is xy, where x goes between negative a and a, and y goes from square root of a squared minus x squared above and down to negative the square root of x squared minus a squared below. Right? In polar coordinates, what's this? Well, how would we describe a circle in polar coordinates? Well, it's going to be all points are theta, where, what do we say about r? The distance to the origin is between 0 and a. Right? So r lies between 0 and a. And what about theta?
Between 0 and 2 pi.
0 and 2 pi. 0, 2 pi. Okay. So a circle is sort of the analog of a square, right? Right? The Cartesian square is basically a polar circle. Okay, everybody okay with that? Okay. Okay. Now suppose we wanted to describe something like this, an annulus. Okay, so the region trapped between two circles. Right? How would you describe that in the Cartesian way? Does anyone want to try? I don't. Okay, let's just leave it. Okay. I'm going to sort of put a grumble here. But polar, right, what is it? So let's say that this is A1 and A2. Then what is it? Well, R goes from A1 to A2, and theta goes from 0 to 2 pi. Okay. So again, it's just a rectangle, right? It's the analog of an annulus is just the analog of a rectangle. Okay. Right, and then there are other things that are more easily described using polar coordinates, so-called cardioids, lemniscates, etc., which are basically described using polar coordinates easily, but not so easily with Cartesian coordinates. So, so here's the idea. Simplify the integral by changing to polar coordinates. So you have some integral that's complicated, but it turns out that, maybe if you express it using polar coordinates, then the domain becomes simpler. Okay, so here's the formula. I'm not going to explain it yet, but I'm just going to give it to you. So f of xy dA over d. Okay, so you have some region, right? So maybe you have something like d is an annulus. Right? Somebody asked to integrate over this annulus. Turns out that you can change that to d expressed in polar coordinates. Of f of r cosine theta So this is the first change of variable, the first change of variable formula for polar coordinates. Change of variable for polar coordinates. Okay. And we'll do. I'm just going to show you how to use it first. Okay. So let's just do some examples first. Do a whole bunch of examples. Example 0, the area of a disk. So there's a disk of radius A. There's a disk of radius A on the plane, and somebody says find the area of that disk. Okay. So the way you do it. So here's this disk. Right. How do you find an area of an object if you're using a double integral? This is can you? Yeah, Phil?
Make the integral where height equals 1.
Yeah, height equals 1. So you integrate the function 1. You integrate the function 1. Just like if you were trying to find the length, if somebody said, you know, what's the length of this interval? You could integrate 1 over that interval, and you get b minus a, the length of it. Right? You integrate this thing, and you're going to get the area of it. Okay. So you know we could do it. We could do it if we wanted, using Cartesian coordinates. But instead, let's change it to polar coordinates. Okay? And so just by using this formula here, it says, well, integrate the function evaluated at these points. But the function is a constant, right? So that function is going to be 1 no matter where we evaluate it. And then we integrate, we have this thing that we integrate against r d theta, right? You say, and the range of theta is from 0 to 2 pi, and the range of r is 0 to a. So you take your region, right? And you say what so this is r a 2. Okay, this is the region that this is the region expressed in polar coordinates. Right? If we took this thing and mapped it through r cosine theta, r sine theta, right? Then this thing would turn into that thing. You guys see that? These guys here, we mapped it through, right? And then it would turn into this thing. Okay, so so let's do it, right? It's easy, right? You end up with well, what happens? You integrate r dr. What do you get? R squared over 2 between 0 and a. Right? Go from 0 to 2 pi d theta. Right? And so you get a squared over 2 times 2 pi. That's the same pi and a squared. Right? Pi radius squared. Everybody see how to do that? Everybody see how to do that? Yeah, a lot.
Why do we need to even integrate it then, if it's just pi r squared? The area of the disk, we just have...
You know that already, is what you're saying?
Yeah.
Yeah, certainly you knew that already. But this is a very simple example of how to use this.
Mm-hmm.
Yeah. So yeah, it's unfortunate. I think on the last exam I gave you some problem, and I was hoping you'd use the chain rule. I gave a simple problem. I was thinking, oh, they'll use the chain rule. But some people just did it directly, realizing that it was very simple to do anyway. The reason I gave a simple problem was just so that I didn't have to get a complicated problem. Yeah.
But if we did have a problem like this, could we just say that the area of the disk can we just say it's pi
If
squared?
I'm so careless as to leave off the instruction, use the change of variable formula.
Okay.
Yeah. Yeah, go ahead. Just yeah, as I was this. Okay. Another example, which again you may know the formula for, the volume of the sphere. Volume of the sphere. But suppose you don't know the volume of the sphere. Or suppose you don't know the formula. Right? Why do you know that formula?
Learned it.
Right, somebody told it to you. Right? But you're not really sure how you got it, right? But now you are.
Mhm.
Now you do. Or at least you do up to a certain point. This you're not so sure about. Certain, yeah. Okay. So volume of a sphere. Suppose again, right? Somebody gives you this half sphere. Somebody gives you half a sphere and says, find me the area of the sphere, so that's twice a half sphere. Twice a half sphere. So that would be the integral over this ball of radius A. Maybe I'll just call it D again. Okay. What's the, so this is A. What's the height? What's the function that we're integrating here? How would you find the volume of the sphere? Think for 30 seconds and write down something. Now you're integrating something over this disk. I mean, if you want, you can do the whole thing. And then with twice the top, you'll get something. Just if you're confused, then think of the analog, right? And how do you find, if somebody asks you for the area of a circle using one variable calculus, right? What integral from negative A to A do you integrate? Integrate the top minus the top. Okay, turn to somebody else and say what integral you have. Please don't talk with Sydney and Sarah. Talk with Sydney and Sarah.
The square root of a squared minus c squared. Minus c squared.
Oh, so she would
What? C being the height.
Okay.
Well, yeah, this is just.
That's like in 2 dimensions. It's just a circle.
So, right, this is a sphere, right? X squared plus y squared
That's not
plus
quite
z squared equals a squared. Right? X squared plus y squared plus z squared equals a squared. That's a sphere, right? And we want to integrate, like, the height, which is z. Right? So what do you get? Anything? What?
Square root of a squared minus x squared minus y squared.
Right, and we'll get 2 of this, right? With this one minus the same thing. Right? If you go from the top to the bottom, right, the z will be, the top z is plus this, the bottom z is minus this. You take the top guy minus the bottom, you get 2 of them. Okay, so again, right, you could try to integrate this, over, as a double integral, but instead we're going to switch it to polar integrals. Right. So again, we get, okay. So we're going to integrate the function evaluated at r cosine theta, r sine theta, right? So we get the function evaluated at r cosine theta, r sine theta. Right? The function evaluated when x is r cosine theta and y is r sine theta times r dr d theta. Right? And we're going to integrate that again over 0 to pi, 0 to a. Right? So what do you get? 0 to pi, 0 to a, 2 times square root of a squared minus r squared, right? Because r cosine theta, r sine theta turns into r squared. R squared cosine squared theta plus r squared sine squared theta turns into r equals theta. Right? That's nice because we have this 2r here. We can use that to integrate. So we get negative the integral from 0 to 2 pi a squared minus r squared to 3 halves. Keep it up.
With the negative people.
Put it in the negative.
It's negative,
From the
negative
negative,
r
from the
squared.
negative r
Oh,
squared,
okay.
right? When you use the chain, when you differentiate this, you get 3 half. Oh, I messed up. I need 2 things here. Right. You get 3 halves times 2/3 of a squared minus r squared to the 1 half times the derivative of the inside, which is negative 2r. So that gives me 2r. So if I change it, right? How do you get that? You get 4/3 pi a cubed.
Why do you add in the r when you switch to polar?
Yeah, why do you add in this r? What is this r? What is this r? Yeah. Does anyone have an idea what this r is? What is this r? Like, let's think like this. What would happen if you didn't add in that r? Oh, yeah.
I think, doesn't it have to do with the r squared and the, like, area? I feel like it has to do with that.
Yes, it is related, actually. Yeah, Sydney.
Does it like give it magnitude?
Does it give it magnitude?
Like it makes it the right length, if that makes sense?
Yeah. Gives it the right length. Well, in this case, it gives it the right area.
Right area, yeah.
Gives it a Paul. Yeah.
Right, yeah. R is pretty much just a scalar, and then if you didn't have R, it would all be on the unit circle pretty much.
Okay, well, not exactly. The closest answer is probably Sydney's, where you say if you it gives it the right area. It gives it the right area. If we didn't have that R in there, Lily, I'll give you a better explanation. I'll give you 2 explanations in probably in this class or in the next class. But just think for right now, if we didn't have that R, and we went back to here, suppose we go back to here, okay, to our first problem. Suppose we don't have that R in there, right? When we integrate, what do you get?
Just r.
Right? And so you're going to integrate, what you're integrating is over this thing, right? And so what you get is going to be 2 pi times a, right? You're integrating, if we integrate 0 to 2 pi, 0 to a, 1 dr d theta, right? That's just the area, right? That's just the area of the rectangle, right? Which is the length times the height. You get 2 pi a. Okay. You get 2 pi a, but you see that you should have gotten pi a squared, right? Right? You got instead of getting the area of the circle, you get the area of a rectangle. Okay. And so that r somehow is a correction factor to adjust the integral at every point at every point, it has to say, I'm actually not integrating over, I'm actually not integrating over a rectangle. I'm actually integrating over some sort of polar sector. Okay, right? The blocks that we're integrating over here actually correspond to these polar sectors over here, right? These polar sectors over here, right? And really, the thing that I'm taking a volume of has height f, but base, the area of the base is the area of that polar sector. Okay, it's not this area. It's actually the area of this thing, right? So at every point, some adjustment has to be made, and this is the adjusting factor. Okay. Yeah. Okay. Sort of an analog. Maybe this is so. I don't know if this is going to help or not, but if you think about U substitution, so recall U substitution. You have the integral from a to b of some function. Right? And using U substitution, you recognize that this is f of u du from g of a to g of b. Right? Okay, so U substitute, this is your old U substitution formula. You take this integral, right? You take this integral, and then you express it as, you know, the integral over some other point. This is exactly this. This thing here is your left-hand side. This thing here is your right. This thing here is the right-hand side. Okay, you're taking the function, evaluated at some point, and then you'd say, well, what's this g prime? This g prime is actually the adjusting factor. It wasn't made obvious to you at the time, but this is actually the adjusting factor to make sure that you're integrating at the right over the right length. Okay. If we look at the transformation, this goes from r cosine theta r sine theta. Right? Here's the transformation. It goes from r theta to r cosine theta r sine theta. If we take the derivative of that, that's a matrix. That's a matrix. Differentiate with respect to r, differentiate with respect to theta, differentiate with respect to r, differentiate with respect to theta. Oops. Right. What's the determinant of this matrix? R. Right. You get the determinant of this thing is going to be this times this minus this times this. R cosine squared theta minus negative r sine squared theta. Result?
I see.
So I could rewrite this thing on the right, actually like this, f of t of y theta, the absolute value of the determinant of the derivative r of t dr dθ. Okay, and now you see the analogy. Right? So the polar coordinates. Or maybe I should write it like this. Something q, and then this thing is tq. Okay, so just to make the analogy more complete. some sense of where does the R come from? Where does the R come from? It's actually the it actually tells you some sort of scaling factor for the area to make sure that the area that you're integrating over is the proper size. Okay. Back to the examples. Back to the examples. Okay, so example 2. Somebody gives you a Cartesian integral, negative 3 to 3, 0 to square root of 9 minus x squared, sine of x squared plus y squared, dy dx. Okay, and somebody says, integrate this. What could you do with it? What could you do with this integral? I mean, it could be useful to see what the domain of integration looks like. Right? Here's x, y, and x goes from negative 3 to 3, y goes from 0 to 9 minus x squared. So it's a circle, it's a half circle. That's our domain of integration, and we've expressed it as an x simple region. Maybe it'd be one trick you could play if you hadn't seen before this class. The only trick we could play is to switch it to the other variable. Right? But you'll find that I'm pretty sure that that's not going to help you much. In fact, it's not going to help you much. But what can we do now? We'd say, yeah, Alana.
You can change it to polar.
Let's change it to polar. Right? So this thing expressed in polar coordinates is what?
It's 0 to 2 pi, or the radius is 0 to 3.
Okay.
And then it is 0 to 2 pi.
0 to 2 pi?
Or just pi?
Just pi. That's all right. 0 to 2 pi. Right. Okay, so let's rewrite this thing. It's going to be r d theta. Theta goes from 0 to pi, and r goes from 0 to 3. Right? And then we're integrating
Sine of r cosine theta squared plus r sine theta squared.
in other words,
R
squared.
squared.
Sine r squared. Right, which is good. So you integrate that however you like. Put a 2.5 here. Get 1/2 the integral from 0 to pi. Negative cosine r squared between 0 and 3 d theta. Right? So, and this thing, right, is just going to be negative 1/2 cosine 9 minus cosine 0 times pi. Okay, any questions? Any questions? Let's do another one. So skipping one of them. So, what's the volume of the solid Above the cone, z equals root x squared plus y squared. And below the circle, x squared plus y squared plus c squared equals 1. Okay, let me give you the intersection. The intersection is above x squared plus y squared equals a half. So the picture is you have this cone going up, right? And you have a circle going down, and they intersect. Right? And you want right, this thing, the intersection is this circle of radius a half. Right? And they're asking you for the volume of this thing that lies below the sphere and above the cone. Okay, looks sort of like an ice cream cone, like a disappointing ice cream cone. What? Right, so take 1 minute and set up the integral in polar form. Okay, turn to somebody else and say what you got.
So there's something weird about it.
Yeah, there's 2 pi. Is it 2 pi? I just said pi. I just said because it's
And then
none
it
of
goes
it's
from just
negative.
0 to 2 pi.
So, okay.
Well, none of the z is negative, but on the xy plane, it's also fine.
Subtract, so
Oh, you're
So
right.
I think that is.
You're right. Well, but yeah, so it's 2 pi because yeah, I was thinking of like the whole thing, but
Yeah.
but d is.
And the function, the function, like one function minus another function.
Yes, that's what I did. I forgot to make these r.
Yeah.
But
minus the square root of x squared plus y
yeah.
squared.
Okay, so you would do the sphere equation.
Mm-hmm.
Okay.
Okay, so who would like to say what they got? Who would like to make a guess?
Square root of
Let's just put it up. R d theta, right?
minus
What's it going to be?
r.
The thetas, here's your domain, right? Here's your domain of integration. You're integrating the top guy minus the bottom guy over this domain, right? So what's the domain? Well, you see r goes from 0 to a half, and theta goes from 0 to 2 pi. Right? And then you take the top guy minus the bottom guy.
Yeah, so what should it be?
Yes, thank you. Sorry. Thanks. Okay. Okay, so then you get the top guy minus the bottom guy. So what's the equation for the top guy?
Z equals the square root of x squared plus y squared minus 1.
Okay, so here we get z equals the square root of 1 minus x squared plus y squared. Okay.
The other one is just the square root of x squared plus y squared.
So here we have
Yeah,
it.
and then
Let's give it a
you
test.
subtract the square root of 1 minus x squared plus y squared. And then, or wait, you subtract the square root of x squared plus y squared from 1 minus x squared. Yeah.
But remember, we have to change it to...
Right, and then you change it to polar, so then you get 1 minus r squared, and then just minus r.
Okay, so it's r. Okay, so that's the integral, and then you would do it. Okay, pretty straightforward, I hope. Okay. Any questions about that? Questions? So I'm going to do one more example. So I could spend the rest of the class giving one explanation of where the r comes from. But instead, I'm going to do an example. It's not that complicated example, and so you can say like, why is he doing this example? It's a famous example, and I think you should know. Okay. So here is a famous integral. Or this leads up to a famous integral. So somebody asks you to integrate e to the negative x squared plus y squared dA over the ball of radius A. Or the disk of radius A. So again, you have the disk of radius A, and somebody is asking you to integrate this exponential function over that thing. So you switch it. You say, okay, well, I'm going to use polar integration on it. So this x squared plus y squared turns into negative r squared, right? So negative r squared, and then we have r d theta, right? And of course, theta goes from 0 to pi, and r goes from 0 to 8. You see that trying to integrate this directly would be difficult. But integrating using using the change of coordinates is pretty simple. And so you end up with this thing, and let me just say what you end up with. You end up with pi times negative e to the negative a squared plus 1. So, and if we let a go to infinity, right, suppose we take this integral over, basically, we're trying to get the area of this thing, the volume of this thing over the whole plane. You see what we get. What do we get? Pi, right? So if we take the limit of the above integral, as a goes to infinity, we get pi. Right? Which, if we write like this, I read it like this, right? Because you can split the e to the negative x squared plus y squared into two separate integrals, right? This gives you a famous result that e to the negative x squared dx actually equals pi. Square root of 1. Right, because these are the same thing. Okay, so this is an integral which you would have no hope of doing in one variable calculus. But you do something funny to it. You say, okay, I'm going to take the integral and multiply it by itself, and then change it into a double integral. Double integral, which I can evaluate using polar change coordinates. Right? So by doing something very complicated, you know, you take this thing and change it into something more complicated, which actually turns out to be more simple. That's it for